This conference will now be recorded.
Hello everyone. We'll start with some problems because we have finished group 13 and before starting group 14, some problems regarding group 13 elements we'll discuss, and after that we'll start group 14, and there we will see the occurrence of group 14 elements, different types of atomic and physical properties such as its atomic size, that is atomic radii, ionization energy, obviously electronic configuration, melting point, boiling point, electronegativity, density, metallic character, then pi bond formation tendency, and also the anomalous behavior of the first element carbon. So let's start with this problem, which is group 13. Beryllium and aluminium. Now beryllium is from S block and aluminium it is from group 13. Exhibit many properties which are similar, but the two elements differ in which property, that we have to find from these four options. But why these two elements, they are exhibiting some properties that are common? What is the reason behind that? The reason is basically diagonal relationship. So if I write group 2 elements, the first element is beryllium, and after that there is D block, and jumping the D block, if I start P block, then the first group is group 13, where the first element is boron, and after that there is aluminium. So if you see, there is diagonal relationship present between these two elements, right? So that is why there is some similar properties, but it is not necessary that all the properties has to be similar. It may not be so. So basically we will find that property in which they are not similar. So the two elements differ in which property. Now look at the properties. The first one is saying that maximum covalency in compounds. Now beryllium, it is basically from second period. Boron is also from second period, but aluminium, it is from third period. And whenever we have third period, there is presence of d orbital, but here we do not have any d orbital. So maximum covalency, whether it is same or not, that is really a question. But let's see the other options, what it is saying. Exhibiting amphoteric nature in their oxides, forming covalent halides and forming polymeric hydrides. Now amphoteric nature in their oxides, that means we have to consider beryllium oxide and we have to consider aluminium oxide, because we have to check the amphoteric behavior of their oxides. So first we have to write the oxides. Okay. Now amphoteric nature means it should react both with HCl, that is acid, as well as base. So if we look at these reactions are for beryllium oxide and Al2O3. So for BeO, it is reacting with HCl forming BeCl2, and with NaOH we are getting Na2BeO2. That means reaction is happening with both acid and base. Similarly for Al2O3 also, it is reacting with HCl as well as NaOH. That means exhibiting amphoteric nature in their oxides. This statement is correct because there is some similarity in properties. Then forming covalent halides. Now halide of Be, that is BeCl2, and halide of aluminium is AlCl3. Now BeCl2, in S block chapter we have seen there is some covalent nature present, because Be, which is the first element of that is group 2 in S block, it is having some covalent character, unlike the other members. As we move down from B to Mg to Ca, gradually this covalent nature is decreasing, but the first element there is some covalent character. AlCl3 also covalent halide. If you dissolve it in water, then it forms some Al3 plus ion surrounded by water molecules, then there is some ionic nature, but as long as it is not in water, its behavior is covalent. Next is, what about the hydride compounds? Now for Be, the hydride is BeH2, and for aluminium the hydride formula should be AlH3 because valence is 3. Now for BeH2 we have this type of polymeric structure, and for aluminium hydride also there is You can see this is the structure of AlH3 where polymeric nature is present. So B, C, D, all these three common, these three properties, they are common in Be as well as aluminium. But maximum covalency, as I have said, in case of beryllium, there is no d orbital, but here we have 3d orbital. It is vacant, that is fine, but valency can be enhanced. So maximum covalency for beryllium, you can expect it can accommodate. There is 2 electrons present in 2s. Now maximum what we can do, we can do this pair of electron, we can break it, that is unpairing we can do, and then another electron that will be in 2p orbital, but after that there is no d. So maximum 4 valency is possible, 1s and 3p orbitals, but not more than that. But for aluminium, where 3s, 3p, and after that there is vacant 3d also, so enhancement of covalency is possible. So that is why the first property, it is not same, they are differing in this property, though these two elements are having diagonal relationship, but they are differing in this property. Which of the following hydroxide is acidic? Now here we also have one S block element, which is calcium. Okay, sorry, it is CaOH whole 2. It is having 2+ oxidation state. Now we know when we consider acidic property of oxides and hydroxide in a particular group, as we move down, gradually metallic character increases. Now when metallic character increases, basic character is also increasing, right? Now aluminium, boron, and Tl, thallium, these three elements, they are from group 13. Only calcium, which is from S block, that is group 2. Now position of calcium, remember, first Be, then Mg, and then we have Ca. So in CaOH whole 2, that is hydroxide of Ca, obviously there will not be any acidic property. And if we write the 3 group 13 elements one by one down the group, first boron, then we have aluminium, then there is 2 more elements, and after that there is Tl, right? There is gallium, but here we have these 3 elements only, and I have written them down the group. These are the positions. Now this is the first element, and obviously from the first element you can expect some acidic character. Okay, but what type of acid it is? BOH whole 3. It is not. It has no ability to donate any proton. In presence of water, what happens? I am writing water molecule in this way because it accepts this HO, and as a result there is formation of this type of structure, 4 HO and 1 negative charge extra, and this H atom of water, it will be removed as H+. So here BOH whole 3, it is accepting HO minus ion, that means it is accepting negative charge. So the behavior of BOH whole 3 here is Lewis acidic type of nature. But whatever it is, after all it is acidic in nature, and that we have to find. So that is why this should be the correct option. Next question. Now read the question carefully. One equation, basically 2 equations are given. Aluminium metal, when it is reacting with HCl, in bracket mention aqueous, then we are getting compound X, and there is formation of a gas which is denoted by P, capital P. And aluminium, another equation, it is reacting with NaOH, and also though aqueous is mentioned, but still some extra water molecules plus H2 is also written. We are getting compound Y, and there is again a gas, capital Q. Now we have to find the incorrect statement regarding above 2 reactions. The first statement is saying that aluminium shows amphoteric character. So in these 2 equations, what you are seeing, that aluminium is reacting both with HCl as well as NaOH. So obviously it is showing amphoteric. It cannot be incorrect. Then both X and Y are water soluble. Now to answer this, once we write all the equations, then only we will be able to understand whether it is water soluble or not. Then gas Q, it is inflammable, and P and Q, they are different. Now P and Q, this may be different or they may not be different, but that will be clear only when we write the equation. Aluminium, when reacts with HCl, there is formation of aluminium chloride and hydrogen gas. Now if I balance it, it will be 6 will be, and here it is 2 and 3. Fine. Now when aluminium reacts with NaOH, you also have to write water. There is formation of, now this reaction in the properties part you can check once more, it is, you can find there. Al with 4 HO minus, that means there will be a negative charge outside this third bracket moiety, and that is balanced by sodium plus ion. Here also hydrogen is produced. If I balance it, it will be 2, 2, 6, though balancing is not required, but I'm just doing it, and 3. So one thing is clear, that in both cases we are getting same gas. This is P and this is Q. AlCl3 is basically X, and this molecule, it is Y. Now P and K, these two are different. Now obviously it is not correct, and that is the option we are searching for, right? So this should be the correct option. And Q is inflammable, obviously hydrogen is inflammable. X and Y, both these are soluble. So even if you have some doubt regarding whether these two are soluble or not, but remember, AlCl3, when it is in water, there is formation of Al surrounded by 6 water molecules. This type of cation is formed. So obviously it is soluble. And even if you are having any doubt regarding option C, but one thing is clear, P and Q, these two are not different. These two are same gas. So obviously B is not correct, and C has to be correct because it is single choice answer, right? So gas P and Q are different. This statement is incorrect, and that is the correct option. Now this question is interesting. For compound having the formula, look at the molecules GaAlCl4. Now GaAlCl4, both gallium and aluminium, they are from group 13, and we have 4 Cl. So 4 Cl means chloride ion, total 4 present. We have to find the correct option. Now the first one is saying that gallium is more electronegative than aluminium and is present as cationic part of the salt. Now if it is salt, then how I should write it? I should write it in this way. See, Cl minus, total 4 ions are present. That means total negative charge, it is basically minus 4. Now to balance this minus 4, we need plus 4 charge, right? Because overall the molecule is neutral. Now if it is plus 4 charge, that we will get from gallium and for aluminium. Now see, if I write the group 13 elements, first is boron, then aluminium, then there is gallium. That means, remember, 2 types of oxidation state we observe for group 13. One is +1, another one is +3. Now the tendency to show +3, it is more when you are with boron and aluminium, but as we are moving down, then +1, that is oxidation state +1, that is also observed sometimes because of inert pair effect. So +1 oxidation state you cannot find in aluminium, never. But +3, it is possible. That is, this is only oxidation state possible for aluminium. So +1 is not possible for +3. Sorry, +1 is not possible for aluminium. So you have to consider +3 charge for aluminium. Now out of 4 plus charge, if it is having +3, so rest of the +1 charge has to be from gallium. The opposite is not possible. Suppose I am writing like this. That is not possible. This one is correct because gallium can show both, but aluminium it can show only +3. Now if it is so, now I will draw the structure of GaAlCl4. So AlCl4, if Al is having total 4 Cl, aluminium is +3, total 4 Cl, that means one negative charge is extra like this. And to balance this, we have to write gallium outside this third bracket. So this is actually the structure. Directly with Ga+, there is no connection with Cl. All the Cl minus associated with Al, and the overall -1 extra negative charge is balanced by Ga+. Now look at the options. The first one is saying Ga is more electronegative than Al and is present as a cationic part. Now here, if the structure that I have just drawn, this is the cationic part, this is the anionic part. In anionic part, we do not have Ga, but in cationic part we have. That means the first option, which is basically combination of two statements. This is one statement, then and, then second statement. So second statement is basically true. But is the first statement is true? See, gallium is more electronegative. We know that when we move down the group, electronegativity decreases. So at a first glance, it seems that Ga is more electronegative. This is not correct, right? But actually, if you look at the electronegativity values, which is already discussed when in the previous or the any one of the previous classes, this is the electronegativity values. There is some discrepancy. So when you move from B to Al, there is decrease, but when you are moving from Al to Ga, there is slight increase. Then again from Ga to indium to Tl, there is slight increase. So it is not that down the group electronegativity decreases. So Ga is basically more electronegative than aluminium. This part of the sentence is also true. So this is actually the correct option, the correct statement regarding this molecule. But as it is single choice, rest of the options has to be incorrect. But why incorrect? Let's see. Oxidation state of gallium in the salt GaAlCl4 is +3. No, this is not true. This is false because it is +1. This is not +3. Third option, Cl forms bond with both the element AlGa, but that is also not true. False. Ga is coordinated with Cl. That is also not true. So only the first option that is correct. So see the logic that I have given. Even if you do not know the details of the structure of GaAlCl4, just apply this logic. That total negative charge coming from 4Cl minus, it is -4. So there has to be +4 charge. And this +4 charge you can get by this combination, not this one. So if it is following this, obviously the structure should be in this way. Okay. So now we have finished the problems regarding group 13, and we can start group 14, which is basically carbon family, because the first member is carbon. After that, this is from second period, third period, 4, 5, 6, 7. Though the last one is actually radioactive, we will restrict our discussion up to lead, not flerovium, Fl. The first element, carbon, these are the period numbers. Okay. The 17th most abundant element by weight in the earth crust. When it is in native state, that means it is in the elemental state. Different types of forms possible. Coal, graphite, diamond, all are basically carbon. These are basically different physics, that is their physical nature is different. That's all. Otherwise, all of them are basically the element carbon. It is also found in combined state and it is very versatile in the form of metal carbonate. Just take the example of CaCO3, MgCO3 like this, sodium carbonate, potassium carbonate. Then hydrocarbon. So organic chemistry, which is chemistry of carbon and hydrogen, is based on this element only. So from this you can understand how versatile it is when it is reacting with some other compound. So because of this versatility, we have separate branch of chemistry, which is organic chemistry. Okay, hydrocarbon. Then we have carbohydrate, naturally occurring molecule, carbon dioxide present in air, etc. Now, as it is very versatile, I have just said that organic chemistry is solely devoted to carbon-based compounds. There are 3 isotopes present for carbon. Now, the most abundant is this one, which is clear from this percentage: 12C, 13C, 14C. Now, out of these 3, the 12C, that is the most common, 98.9%, 13C 1.1%, 14C is very, very less. The next element, which is silicon. Silicon is the second most abundant element by weight in the earth crust. How it occurs? It occurs in the form of silica. Now, silica, when we are saying silica, there are many forms like sand, quartz, crystal. There is also silicate minerals. If you are having some that is question regarding silica, silicate, there will be separate discussion for this type of compounds. Once we'll finish their physical properties, atomic properties, chemical behavior, then there is some special compounds of group 14 elements. Under that heading, we will have discussion related to silica, silicate minerals. Okay, so silicate minerals, clay, there is also presence of silicon, and there is also these silicate minerals and clay, they are actually the important source for silicon. After silicon, we have germanium, tin, and lead. So germanium occurs in traces mainly recovered from flue dust. So flue dust is basically finely divided metals or any metallic compounds that we get in, that is escape from metallurgical furnace, right? So in those metallic finely divided powder or particles of metal, there is traces of germanium mainly recovered. Okay, and in metallurgy, during roasting of zinc ore, then coal ash, which is coal combustion residuals. So during those processes, the flue dust that is appearing, from this flue dust we can get traces of germanium. The next element is tin, Sn. So Sn occurs mainly as tin stone, which is also having another name, cassiterite ore, and the main composition is tin dioxide, SnO2. After tin, we have lead. The principal ore of lead is galena, cbse, and others are anglesite, which is lead sulfate, and cerussite, which is lead carbonate. So different types of ores of lead you can see here, which is galena. Then we have anglesite. Sometimes see why the names I have given here, because you can get some this memory type based question, simple. So suppose some names are given and it is asked that among these which one is ore of lead. So then you can answer this question. Okay. So for tin, it is tin stone or cassiterite, and for lead it is galena, anglesite, and cerussite. Fine. Next we will see the electronic configuration of group 14 elements. Here the first one, atomic number is 6. Now when it is 6, the last noble gas is helium, having atomic number 2. The total number of electrons 2 is already there. Out of, that is, rest of the 4 electrons, it will be in 2s2 and 2p2. So helium is basically 1s2, period number 2. The next one, silicon. Now atomic number, it is easy to remember. What you have to do, you just have to add 8. Why 8? Because it is 2s2 2p6, 8 more electrons will be added, then you will get 14. So that is why 8. Now when it is silicon, atomic number 14, the last noble gas is neon, having 10 atomic number. That means 4 more electrons you have to place in 3s3p, 3s2 3p2, and period number is 3. The next element is germanium. Now what you have to do, you have to add 18 electron. Now why 18 electron? Where from it is coming? It is because of obviously 8 plus 10 more d electrons. So that is why it is 18. Now after this is 8, 18, and when you are moving, when it is 32, the last element noble gas is 18. Now 32 minus 18, if you do, you will see 14 more electrons you have to place. And after argon, the next you have to fill is 3d, then 4s2, 4p2. And when from germanium you are moving to tin, then again we have to add 18 electrons. So 8 plus 10 d electrons. So why I am saying so, because it will help you to remember the atomic number. Suppose the first one, we all know it is 6. Now the next element, when you will move, you have to add 8. Then for the next 18, again 18. And when 10 to late, now you have to add 32. Now why it is 32? Because 14 f electrons and 10 d electrons and 8 electrons coming from s and p. So if you add it, you will see it is 32. So from 50 to 82, you can get it by adding 32. Now look at the configuration. 50 for T atomic number. The last noble gas is krypton, having 36 atomic number. So after 36, if you subtract 36 from 50, you will see 14 more electrons. So that we have placed here. Then for lead, 82, the last noble gas is xenon, 54. If you subtract 54 from 82, you will see you have to place these electrons extra. So after xenon, there will be 4f, 5d, 6s2, 6p2. But one thing we have seen which is common, and that is the configuration in the valence shell. So what you can say now, this is the common part, how we can write the general configuration. For group 14 elements, it should be like this. Now n value may vary. When it is period number 2, then it will be 2s2 2p2, then period number is 3, then 3s2 3p2, 4s2 4p2. In this way it will move. Fine. So next we will see carbon and silicon. If you look at the code for carbon and silicon, after noble gas, that is noble gas code is there, and just after that you have this configuration NH2 NP2. If you consider the next two elements, that is germanium and tin, so for these two, if you look at this part, here you have noble gas core plus 10d electrons core. So it is core because why I am saying it core, because it is fully filled, so that is why it is core. Okay, and this part is common. So before the common part, we have noble gas plus 10d core, and for the last element Pb, we have noble gas, after that 4f electron core, and then we have 10d electrons. Okay, so these are the information regarding the electronic configuration. After electronic configuration, we will see the size, that is atomic radii of group 14 elements. So in this graph, we have total three groups. As you can see, the red line, that is for group 2, right? Now the blue line, boron, aluminium, it is for a group 13, and the green line, that is for group 14. So all the three lines, you can compare it in the same image. Carbon, boron, beryllium, it is from second period, then MgL, Si, gradually the number of period that is increasing. Now if you look at this atomic radius value in picometer, which is in y-axis, as we know, when we move from group 2, then there is D block, but jump to P block, group 13, group 14, that is you are moving from left hand side to right hand side in the periodic table, the size will decrease, which is clear from this. But how it will vary when we are moving down the group? So in group 13, in P block, that is this chapter, we have already seen when we move from aluminium to gallium, you can see this type of changes are there, and it is because of this D block contraction. Now the same type of thing you will also observe when you are moving from silicon to germanium, and the reason is same. But obviously the radius is lesser than group 2, which is clear here. The radii of group 14 elements lesser than that of group 13, and that is expected because we are moving from left hand side to right hand side, so size will decrease. That is it is expected. And the increase from carbon to silicon, this increase is considerable. The difference is quite fine, but after which the increase, there is increase, but the increase is very, very less. Okay, and it is because of this poor shielding of D and F orbitals. So for this jump, silicon to germanium, it is for D block, but after that there is also, that is for tin and PB, if you consider, there is also introduction of F orbitals, which is clear, which will be clear from this image. So this image we have already seen in the previous group discussion, that is group 13. So this is group 13, but if I write the elements of group 14, carbon, Si just beside aluminium, then we have Ge, we have tin, we have Pb. So see, when it is germanium, just before gallium in the D block, when it is ended at D block here, 3D subshells field. When it is tin, then 4D field. When you are moving from tin to lead, in between there is also 4F. Now these F and D orbitals, they are screening property is very poor. So that is the reason now the nucleus, it will attract the outermost electrons, and as a result size will shrink. Okay, so the expected increase is not there. There is increase, but it is not according to our expectation. Only from the jump from carbon to silicon, it is considerable because there is no intervening subshell present. Fine. Ionization enthalpy. If we compare the ionization enthalpy of group 14 elements, that is greater than the first ionization energy of group 13. And again it is expected. Why it is expected? Because group 14 element size is small. It is in the right hand side of the group 13 and also greater nuclear charge. So this observation is expected. Now what are the values? You can see the values here. From carbon to silicon, from 1086, now it is gradually, it will decrease, and see the first jump is very high, the difference is very high, but after that it is decreasing, but it is not so considerable decrease. So from carbon to silicon it is decreasing, then it is also decreasing, it is silicon, it is Ge, it is carbon. So 786, 762, there is decrease, but not so high difference. Then from 762, 708, this is for this is for tin. But from tin to lead, there is slight increase, 708, 715, which is the discrepancy. So that is why, see, after germanium we have written Pb. So in this part, it is not according to our expectation. And again, the reason is the introduction of D and F orbital. So we can say the decrease from carbon to silicon is very sharp, while there is slight increase in Pb when you are moving from Sn. So from Sn to Pb down the group, our expectation is it should decrease, but it is actually increasing, though it is very slight increase. And the reason is Pb has greater ionization energy. Why? It is because of considerable increase in nuclear charge. And again the same picture I will write here. So carbon, silicon, germanium, tin, lead. So when we have lead, just before it we have 4F and 5D subshell field, and they are having poor shielding capacity, and it is outweighing the increase in atomic size. So what it means? It means that we know that when we are moving down the group, there is size increase, and size increase means what? You can easily remove the outermost electron, right? It is far from the nucleus. So for increase in atomic size, ionization energy decreases. That is one factor, but there is another opposing factor, which is poor shielding of D and F. So these two opposing factors, if one factor is overcoming the other, it will win. So here this poor shielding capacity of D and F, it is overcoming or outweighing the other factor, which is increasing atomic size, and that is why we are getting this type of discrepancy. Okay. The next atomic property, electronegativity, and physical property, melting point, boiling point. Electronegativity of group 14 elements greater than that of 13. Again, it is expected. Why? Because we know when we move from left hand side to right hand side, this is left hand side, this is right hand side of the periodic table. Obviously, electronegativity will decrease. So that is why, electronegativity will increase because non-metallic character gradually increases as you are moving towards the right hand side of the periodic table. Fine. Here we have the values. That is the electronegativity values. As you can see, 2.55. Then down the group, there is normally what happens? Down the group, metallic character increases, electronegativity decreases. But there may be discrepancy because see why we are having so much discrepancy. The main reason is basically poor shielding effect of D and F, right? So when this is the main reason for which atomic size variation, it is not as expected. Because of that, ionization energy variation is not according to our expectation. So it will also have effect on electronegativity variation down the group. So don't think that it will be smooth decrease. That is expected. Down the group, what do we know? Metallic character increases, that means electronegativity decreases. But it may not be always so. So from when you are moving from carbon to silicon, there is decrease, fine, but then there is slight increase. Then again slight decrease and then again increase. Okay, so it is not smooth variation. Then we will see melting point and the boiling point for group 14. So this is group 14. Here the blue line, that is for MP melting point, and this is boiling point for both are for group 14. Now for carbon, these values are very high, and down the group, though it is not smooth, but there is overall decrease you can see. So for melting point, it is decrease. There is slight discrepancy 505 600 in Kelvin when you are moving from tin to PB. Otherwise, it is decrease. And the green line, which is for boiling point, there is decrease, but the silicon and germanium, there is some discrepancy. Otherwise, it is decrease, more or less decrease, but there is some discrepancy. The MP and BP of the first three elements, that is carbon, silicon, germanium, look at the values. They are more than 1000. And also for tin, the boiling point is very high. But especially these three, both MP and BP, significantly high because they are having very stable solid structure. Okay. So when we will discuss later in this chapter some compounds of carbon and silicon, you will be able to understand why their structure so stable and solid. Just take one example, a diamond of carbon, which is really very stable and solid structure. Down the group, MP decreases with one discrepancy due to decrease in interatomic forces of attraction. So what happens when you are moving down the group? Suppose for carbon, 2 carbon or atom, if I see, if it is sized like this. Now when you have reached PB, the sizes are very large. So what happens when the size of this atoms are very high, the interatomic forces of attraction that actually decreases, and as a result melting point also decreases. Now here we also have this table which is just for comparison purpose. So this table is for the elements of group 13. Look at the melting point in Kelvin and also the boiling point so that you can compare. So what you are seeing here, just take boron, its melting point 2453. Now for carbon it is 3823. I'm just comparing same period elements because that we should do. When you are comparing, you should fix the period. So carbon and boron both are from second period. If you compare melting point, boiling point, see for carbon it is very high compared to boron. Then for the next element also 9332740, but for silicon these two are high. The same thing you will also observe for other elements. So overall, in general, you can say if you compare the MP and BP, group 13, group 14, it is high in case of the group 14 element, which is clear from these values if we compare. Density and metallic character. First, look at the density values for group 14 elements. Density values at STP in gram per centimeter cube unit. As we are moving, it is not very very smooth increase or decrease. First there is decrease, then again increase, but maximum is density, it is for lead. If we compare the densities with the previous group, that is group 13, they are more or less same. Now you can compare. So for group 13, again the density in same unit, you can compare. Here also for the last element it is very high, and these two are, see, it is almost same, right? Only carbon and boron there is some difference, otherwise it is we can say they are comparable. Now they are less electropositive. Now come to metallic character. They are less electropositive. This first point is related to density. The second point, they are less electropositive and hence less metallic compared to group 13. Again, it is expected because 14 is just in the right hand side. So non-metallic character will increase, metallic character will decrease. So they will be less metallic, less electropositive, right? Because their sizes are small, ionization energy is high. So less metallic character, less electropositive. And when we are moving down the group, which group? Now we are talking about group 14. When you are moving down the group 14, metallic character increases, and that is again according to our expectation. So this is group 14. The first element, it is non-metal. The next element is also non-metal. Now for germanium, the middle element, it is having some metalloid character, in between character. And again for tin and lead, these two are metal. So from this, you can understand that metallic character is increasing down the group, which is clear, right? So density and metallic character. After that, now all the physical and atomic properties we have seen. If we summarize it, then we will see this, look at this table. First of all, the physical state. Now all these are basically solid when it is 298 Kelvin. Atomic mass, it is more or less double the amount of atomic number, though it doesn't follow always, but more or less double. Then atomic radius, how it changes, that we have seen. From 77 in picometer, this jump is very high, but after that there is slight increase. Okay. Now this ionic radius, we have not discussed it, but here you can see, because it is not exactly, we should not say ionic, because free ion of M4 plus. M means in general the element M, it means any group 14 elements. It may be carbon 4 plus, silicon 4 plus. So in general, if we consider ionic radius, now this part is not very important because free ions like C4 plus, they do not exist. So that is why, see here it is mentioned, star sign is there for 6 coordination, except for these two, because here 4 coordination is possible. So it is not exactly ionic radius, you can say, because they do not form ionic compound. But what you can say, that when they are having oxidation state 4+, even if it is covalent compound, if the oxidation state is 4+, so maximum you can consider 4 coordination. But for other compounds, 6 coordination possible, because these two are very small elements, size is very small, the first two elements. So they cannot, that is surrounding this small size C4+ or Si4+, 4 coordination is fine, but 6 coordination it will be very high. Then look at the values, it is near about 29 or near approximate values are there. So down the group, the size is increasing, and that is expected. Now ionic radius for M2+. Now M2+, sometimes we can get free ion, because M2+ compared to 4+, it is more ionic in nature. Okay. And down the group, as we know, metallic character is high. So free metal ions you can get. And see, these two are, it is not possible at all. These two are also very rare. So that is why there is some approximation sign. We cannot expect free ion for the first two elements, because they are actually non-metallic in nature. Okay, they mostly form covalent compounds, not ionic compounds. But down the group, you can get Pb2+ ion or Tin2+ ion, because now metallic character is there. So for this, that is M2+, which is not possible for carbon and silicon, but possible for the next two elements. Here in picometer, look at this double star. This is for coordination. So when there is 6 coordination compounds they are forming, then this is actually the average values, because they can coordinate with different types of groups or atoms or ions. So if several of these compounds are taken, and if we take the average value, so these are those values. Okay, but mainly just remember this atomic radius part. This is the most important. Then some more properties. First, ionization energy, we have already seen it. We have also seen the electronegativity. It is not that down the group there is decrease, there is discrepancies. Then melting point values we have seen, though here it is in degree centigrade, but we have seen in the previous slides in Kelvin only. Unit is different. Then density, gram per centimeter cube. Now see, here it is mentioned graphite, because when I am saying density of carbon, carbon can remain in native state in different types of allotropes are there. What is allotropes? Detailed discussion will be done separately. But right now just see, graphite is one of the allotrope of carbon. But if you consider diamond, there will be different types of density. So only so that is why specifically it is mentioned that for which allotrope we are talking about the density. Then for tin also there is some other forms. So it is a white tin for which density is mentioned. Fine. And we also have this reduction potential value, which is very important, because based on this you'll be able to understand their reducing tendency or oxidizing tendency. Now it is for which oxidation state? EO2. E means any group 14 elements. EO2 means what? For each oxygen it is -2 charge. That means 2 oxide means it is -4. That means here oxidation state of E is +4. So from E4+, when it is accepting 4 electron, we will get neutral E. So for this system, the reduction potential values are basically given, and as it also changes depending on you have taken basic solution, acidic solution, or neutral solution. So specific informations are there, that for E4+ E system, how we write it? We write it like this. First oxidized state, then reduced state. In between there is oblique sign. In acidic solution, the values you can see here. Okay. So here we have the summarization for all the physical and atomic properties, right? Oxidation state of group 14 elements. Now, if you want to get free, I am writing in as E, where E may be carbon, silicon, germanium, anything. If you want to get free ion like this, then you have to provide all these ionization energies. Now, if you take the summation of all these ionization energies, it will be very high, right? So that is the reason free ion like this, it is not very common. It is not possible because energy requirement is very high. So that is why when you consider +4 oxidation state for them, it is mostly covalent in nature, because covalent nature means what? Covalent bond is there, and in covalent bond there is proper sharing of electron. Oxidation state we write 4+, and that is based on with what type of other compound it is forming compound. So suppose E is forming compound with oxygen, and oxygen is obviously more electronegative. So in this covalent bond, you will place negative charge over oxygen and positive over E, because oxygen is more electronegative. So that is why oxidation state is +4, but that doesn't mean that it is in free state. So don't think that it is simply the oxidation state. But they will form compound which is covalent in nature, and the reason is energy requirement is very high if we want to get 4+ ion. Okay, 4+ ion means you have to completely remove all the electrons. Ionic compound means what? Complete donation of electrons from the one element, and other element is completely accepting. So that is why there is cation and anion, but that is not possible here, okay, because of high energy requirement. And why we are talking about +4 oxidation state? Because just think about the general electronic configuration. It is NH2 NP2. That means total 4 electrons they can take part in reaction, right? But because of inert pair effect, +2 is also possible for the heavier elements. So +2 tendency, +2 oxidation tendency will be high for maximum for Pb obviously, but for these three, +2 is observed. In tetravalent state, the compound of these elements are electron precise. Now what it means? So suppose E, which is the general way we have considered group 14 elements. So suppose it is forming compounds with halogen. Let's take Cl minus. So the formula is ECl4. Now E is forming total 4 bonds with chlorine. Why I am saying it is electron precise? Because if you consider the total electrons surrounding E, which is group 14 element, it is basically 8 electron. So octet is common, it is not extra, it is not less than that. So that is, it is electron precise. So here electron accepting tendency, that is the Lewis acidic tendency that you have seen in case of the previous group, that is group 13, that type of property will not observe here. So there is no, because there is no extra electron, there is no deficiency of electron, so they will not be electron donor, they will not be electron acceptor, they are electron precise. That exact amount is already there. Now the tendency to show +2 oxidation state, it is mainly observed in these three elements, and maximum is for Pb, then Sn, then germanium, and that is because of inert pair effect. Inert pair effect in general, it is discussed probably in the first class, so you can check it there. Okay, and when we have +2 oxidation state and just compare with +4 state, so obviously +2 state, that is a lesser positive state, that is always more ionic than the +4 state. Okay, carbon and silicon mostly show +4 oxidation state, which is you can see in this table, and sometimes, which is very unique for carbon, it can also show negative oxidation state unlike other members, because if you consider electronegativity, it is more electronegative than the other members. Now negative oxidation state, one example if I give you, you can consider methane, which is very common organ, that is the first member of alkane in organic chemistry. So in CH4 you have total 4 carbon hydrogen bond, and if you consider electronegativity, carbon is more electronegative. That means here positive charge will be over carbon, sorry, negative charge will be over carbon, positive will be over hydrogen. So here oxidation state is -3. This is just one example. There are more other examples. So it is easy to understand that when carbon will show negative oxidation state, you just have to check that the other element with which carbon has formed the bond, whether that other element is more electronegative than carbon or less electronegative. So just you can see hydrogen is less electronegative, so that is why carbon is negative. Similarly, when carbon will form bond with oxygen, now there will be positive over carbon, negative over oxygen. So it depends with which it is forming bond. If you know the electronegativity of the elements, which one is high, which one is low, you can easily find the oxidation state. And you will be able to understand in which compounds carbon is showing negative oxidation state. There are many organic compounds, but the overall oxidation state of carbon, it is negative. Then germanium forms stable compounds in +4 state, and few compounds are there in +2. That means for germanium, +4 is more it is prevalent than the +2. Then for Sn, the next element, it can form compounds in both states. But remember one important information: when it is in +2 state, it is actually a reducing agent. It means what? When it is in +2 state, it is reducing agent. That means it will lose electron and it will be converted to Sn4+. So this tendency is very high. So it is another way of saying the tendency of Sn is more to remain in Sn4+ state rather than Sn2+ state. Okay. Now if I write it in opposite reaction, that is Sn4+ accepting 2 electron, it is converted to Sn2+. Because when we consider reduction potential value for any system, we always write in this fashion, that is the oxidized species accepting electron. That is, we always write the equation in reduction form. So that is why I have just written the reverse equation, and for this system the reduction potential value is 0.15 volt. So this value is very low. Okay, so this value is very low. That means here this accepting tendency of electron, it is not very high. That is the tendency of Sn4+ to take 2 electrons so that it can be converted to Sn2+ state. That tendency is not very high, which is clear from this value. What about lead, the last element? It will prefer +2 state, and it is because inert pair effect is maximum here. So that is why when lead is in +4 state, it will behave, it is like a strong oxidizing agent. It means what? Suppose we have Pb compound in 4+ state, it will have a tendency to be converted to Pb2+ state by accepting 2 electron. Why? Because it is strong oxidizing in nature, and the tendency to remain in Pb2+ form, it is because of inert pair effect. So it is solely because of inert pair effect, but that same logic you cannot give for Sn, because here the reduction potential value also we have to consider. So which oxidation state it will behave as reducing or oxidizing? It is not, it is basically influenced by so many factors. So you just cannot consider one factor. So other factors also sometimes is playing role. So for Sn, it is the tendency, when it is in 2+ state, it will have a tendency to give 2 electron to other species and itself converted to Sn4+. So you can say its behavior is opposite to that of Pb system. Okay. So we are at the end of this session. Next day we will see some problems and further discussion of group 14. We are ending the session here. Thank you for listening.